In 2013, the sky erupted over Chelyabinsk, Russia. A massive meteor entered the atmosphere and detonated with zero warning. It was chance that this rock didn't detonate over a densely populated city center. We avoided a mass casualty event that day by luck. Fast forward to late 2024, when astronomers discovered something far more intimidating: asteroid 2024 YR4. At roughly 60 meters wide, it easily qualified for the title of a city killer. This diagram illustrates the sheer scale of a 60-meter asteroid compared to a typical city block. If a rock this size hit Earth, the kinetic energy released would equal 500 Hiroshima bombs detonating at exactly the same time. We cannot rely on getting lucky forever. Finding 2024 YR4 forced us to face exactly how exposed our planet actually is. When astronomers first tracked YR4, the math was alarming. They calculated a 3.1% probability of it hitting Earth. Even after further observations ruled out a direct hit on our planet, a new problem emerged: a 4.3% chance that it would slam into the moon in December of 2032. But by the spring of 2025, we lost it. The asteroid drifted into the glare of the sun, and our ground-based tracking networks went totally blind. The problem lies in how we look for these rocks. Ground-based telescopes rely on visible light reflecting off the asteroid. If a dark, charcoal-like rock is positioned near the sun, it simply vanishes against the glare. We were looking at a strict countdown to 2032, and the target was completely out of sight. So if a rock like YR4 was actually headed our way, what could we do? Well, we actually have a defense mechanism successfully tested by NASA's DART mission. In September 2022, NASA sent an autonomous spacecraft to intentionally crash head-on into an asteroid named Dimorphos at over 6 kilometers per second. This diagram shows the baseline physics of kinetic deflection. When the spacecraft hits, it transfers its forward momentum to the asteroid. But the real power comes from a concept called the momentum enhancement factor, or beta. Beta is a metric that measures how much the total force on the asteroid is multiplied by the impact. As the collision blasts a massive plume of rock and dust out into space, that debris acts exactly like a rocket thruster. It pushes back against the asteroid, multiplying the total deflection force. These images show the massive glowing ejectatail streaming off the asteroid after the DART impact. That thrust was so powerful, it shortened the asteroid's orbital period by 33 full minutes. We proved we have the brute force physics to physically knock a city killer off course. But that weapon is completely useless if we can't find our target in the dark. That brings us to early 2026, and a highly unusual plan to hunt down the missing YR4 asteroid using the $10 billion James Webb Space Telescope. Pointing Webb at an asteroid is incredibly difficult. It was built to stare at stationary galaxies billions of light years away, not to track tiny, fast-moving space rocks zipping through our own solar system. To find it, scientists used Webb's near-infrared camera, an instrument that detects heat instead of visible light, to run a fully blind synthetic tracking search. This is a computational method that scans for the faint thermal glow of an asteroid against the freezing backdrop of space, even when we don't know exactly where it is. Tracking YR4 required pushing the most complex scientific instrument ever built to its absolute limit, temporarily turning a deep space observatory into a high-tech planetary defense radar. The gamble paid off. In February 2026, Webb successfully captured the incredibly faint thermal signature of 2024 YR4. This orbital map shows the updated trajectory. With the highly precise data from Webb, astronomers locked in the asteroid's exact path and definitively ruled out a lunar impact in 2032. It will safely bypass the moon by over 21,000 kilometers. The immediate threat is gone. But because YR4 will fly past us again in 2028, it gives us a perfect live target opportunity to test and calibrate our detection networks. And soon, we won't have to borrow deep space telescopes to do this job. NASA is developing the NEO Surveyor, a dedicated space telescope designed specifically to orbit Earth and hunt for hidden asteroids using infrared light. By pairing the ability to spot invisible threats in the dark with proven kinetic deflection technology, we are no longer just waiting for the sky to fall. We are actively guarding our planet.